So we are turning in assignment 4 today. I posted the test when, end of last week or something? The test, anyway, the first take-home test is posted due a week from today. So I thought first what I'll do is throw it out to you all and see what questions you have on the assignment due today, or on if you've started on the take-home test. I'm happy to entertain those questions as well. I know some folks have already turned in the assignments, so I don't know if there are many questions left over on those. And give me 1 second. Okay, well, if there are no questions, then we'll just go ahead and get started. We're finishing up Chapter 2, and this section on congruence relations is the last bit that's included on the take-home test. If we have time, we'll get a start on the next chapter, which isn't a part of the take-home test, but will be a part of the next assignment whenever we get that. All right, so we're looking at congruence relations, and back in another section, when we were looking at equivalence relations, we said, let's look at the relation where it's a relation on the integers, and we say that A and B are related, or A is related to B, if A minus B is a multiple of 5, right? I think this was sort of basically kind of how it was laid out. And we showed that that is an equivalence relation. We showed that it was reflexive, symmetric, and transitive. And as it turns out, this is a special kind of equivalence relation. We call it congruence relations. So we would say that, like, for example, 6 and 11 are congruent modulo 5. This is congruence modulo 5. And in fact, it's if I replace 5 with any other positive integer, that is also an equivalence relation. So we're looking at these types of equivalence relations, which are congruence relations. And it's pretty typical to use like a triple equal sign, like equivalent mod 5 or congruent mod 5, but really depending on the book, people might just use the regular double equals and not a triple. It means the same thing. It's kind of just what people prefer to write. So a lot of the time you'll see it written as A equivalent to B or congruent to B, and then mod n in parentheses. Another type of notation is to write the little triple equals with a subscript n. Those mean the same thing. So this relation is an equivalence relation for any fixed n, and we're just going to show that right off. So we're going to show that it's reflexive, symmetric, and transitive. It doesn't take very, very long. That's why there's not a whole lot of space devoted to it in the notes here. But A is congruent to A mod n for every integer A. So let's prove it. This is a one-liner. Let's let A be some integer. And let's observe that A minus A is equal to 0, which is a multiple of n. That's n times 0. So A is equivalent to A mod n. It's reflexive. So we've got that done. Part B. We're going to show that it's symmetric. So part B says if A is congruent to B mod n, then B is congruent to A mod n. So let's let A and B be integers. And suppose that A is congruent to B mod n. That gets us something, right? The way that this relation is defined, that means that A minus B is some multiple of n, so is equal to n times k for some integer k. We want to show that B is congruent to A. So the way the relation is defined, we're going to look at the difference B minus A, and we'll observe that B minus A is the negative of A minus B. And of course we know that A minus B is nk, so this is negative nk, or n times negative k. So that means that B is congruent to A mod n. So this last one, if A is congruent to B and B is congruent to C, then A is congruent to C. Excuse me. Thank you. So we're going to show that it's transitive. So we're going to let A, B, and C be integers. And suppose that A is congruent to B mod n, and B is congruent to C mod n. We're going to show that A is congruent to C. But what we get from our two assumptions, right, since A is congruent to B mod n, we know that A minus B is n times k, and B minus C is n times j for some integers k and j. Right, we're just kind of recreating the argument that we already wrote for the specific equation for congruence mod 5 back, I guess that would have been in the last chapter. We want to show that A is congruent to C, so we have to look at the difference A minus C. Does anybody remember how we rewrite this? Like the trick that's involved to show that this has to be a multiple of n? It's been too long, is what I've heard. Yeah. So it's a simple trick, but not always one that pops up or obvious to us to try. We're just going to subtract and add the same thing. So this is the same as A minus B plus B minus C, right? So we just added 0 in the middle there. And that's helpful because we get to kind of look at it grouped in those two ways. A minus B we know is n times k. B minus C is n times j. And now we're going to factor out the n. So A minus C is a multiple of n, which means that A is congruent to C mod n. Okay. So when we have an equivalence relation, remember we said once we have an equivalence relation, that defines a set of equivalence classes, right? We have an equivalence class of an element of your set, and the equivalence class of an element is just all the elements that are equivalent or related to it under your equivalence relation. We spent a while proving that the equivalence classes of an equivalence relation partition the set. And in fact, having a partition of a set is equivalent to having a set of equivalence classes for some equivalence relation. So this is an equivalence relation on the integers. So once you pick an n, if you fix an n and look at congruence modulo n, those equivalence classes partition the integers. So the set of equivalence classes, which we might call Zn, or sometimes you use the Blackboard bold n, Z sub n, or Z mod nz. So that's how we say this, is Z mod nz. They refer to the same thing. They're just the set of equivalence classes, or the set of integers mod n. So we're going to write out the equivalence classes for congruence mod 3. So what are all the integers equivalent to 0? So congruence mod 3, we'd say that A is congruent to B mod 3 if A minus B is a multiple of 3. So the integers that are congruent to 0 are the ones, are any integer A such that A minus 0 is a multiple of 3. Any integer such that when you subtract 0, you get a multiple of 3. It's just going to be the multiples of 3. 0 is a multiple of 3. I'm going to write out all the other multiples of 3. There are infinitely many. An integer that's not represented in that set is 1. So let's find the equivalence class of 1. Again, I'm going to, if A is related to 1, that means A minus 1 is a multiple of 3. Or in other words, A is 1 more than a multiple of 3. These are all the integers that are 1 more than a multiple of 3. So negative 8, negative 5, negative 2, 1, 4, 7, 10, and so on. 2 is not represented in either of these sets, so we'll find the equivalence class of 2. If you're equivalent to 2 or related to 2, that means A minus 2 is some multiple of 3. Or in other words, if you do a little algebra, A is going to be 2 more than a multiple of 3. So that brings us to negative 7, negative 4, negative 1, 2, 5, 8, 11, and so on. Right? So there's each of these sets is infinite. So I got an equivalence class of 0, 1, and 2. The equivalence class of 3 brings me back up to 0 again. So every integer is represented in one of these sets. Right? These partition the integers. Every integer is in one and precisely one of these sets. So we wrote out sort of the equivalence classes. Each one of these the 0 bracket, the 1 bracket, the 2 bracket represents a set of infinitely many. But what we're going to do now is sort of represent it and say, okay, Z mod 3Z as a set contains the equivalence class, these equivalence classes, the equivalence class 0, 1, and 2. Now I write this as a remark later on in the notes, but I'm going to do it right off the bat now, but just because it's convenient notationally. Instead of doing brackets all the time, it's pretty conventional to just use like a little overline. So 0 bar, 1 bar, 2 bar. So it looks like, Z mod 3Z is like a finite set, right? There's a finite number of equivalence classes. We think of it as a finite set of 3 things, but what we should keep in mind is each one of these 3 things represents a set of infinitely many things. Okay. So some properties of these congruence relations. If A is congruent to B mod n and C is congruent to D mod n, so we fix an n and we have like A is congruent to B and C is congruent to D, then A plus C is congruent to B plus D, and also A times C is congruent to B times D mod n. Also, if A is congruent to B mod the product mn, then they have to both be congruent mod m and congruent mod n individually. We're going to prove the first part. The second part is actually not difficult. It might show up on one of the exercises. We'll sort of show how we go about doing the first one. So let's suppose that A is congruent to B and C is congruent to D. That gets us some things, right? That allows us to write a couple of equations. If A is congruent to B mod n, that means that A minus B is some n times k. Or, in other words, just rewriting this, A is nk plus B. And similarly, since C is congruent to D, C minus D is n times j, or C is n times j plus D. Right, that there are these integers k and j that exist that make this true. I've decided to rewrite them the way I did over here on the right side because we're trying to show something is true about A plus C and B plus D. Right, and then also A times C and B times D. It'll be helpful to have these expressions for A and C individually. So let's make some observations. I'm going to focus on the first part, showing that A plus C is congruent to B plus D. So let's look at A plus C. A is nk plus B and C is nj plus D, so I'm just going to substitute. So nk plus B plus nj plus D. I'm going to just rearrange the terms on the right side. So I've got B plus D, I'm going to put that first, plus nk plus nj. And now from those last two terms, I'm going to factor out an n. So the sum A plus C is now B plus D more than a multiple of n. Or, in other words, if it's helpful to think about it this way, A plus C minus B plus D is equal to n times k plus j. Right, when I subtract them, I get a multiple of n, and that means that they are congruent. That was the first part. Then they asked us to prove that A times C is congruent to B times D. So over on the other side of this line, let's look at the product, A times C. And again, I'm just going to use these substitutions here, right, that we came up with. So I'm going to multiply them. I've got nk plus B times nj plus D. And well, now we'll do some good old-fashioned algebra. Let's FOIL this out. Nk times nj plus nj KD plus NJB plus BD. We're trying to show that A times C is congruent to B times D. So I'm going to like just observe or kind of notice I've got this product B times D at the end. I'm not going to do anything with that right now. But this other stuff in front, everything has a factor of n. So I'm just going to take out an n. And then we have NKJ plus KD plus JB. So here we have the product AC is some multiple of n plus BD. Or in other words, if you like, we could subtract the BD from both sides so that we have AC minus BD is a multiple of n. And that is precisely what it means to say that AC is concurrent to BD. Questions? So just to kind of illustrate what we're talking about here, we'll just note that 1 is congruent to 7 mod 3 and 2 is congruent to negative 4 mod 3. It's important that they're both mod 3, right, that we've got the same modulus each time. And what theorem 217 says that if I take 1 plus 2, that's going to be the same as 7 plus a negative 4 mod 3. And of course this doesn't take long to realize because of course they both give us 3. They're both equivalent, in fact, both congruent to 0 mod 3. And also, so that was the first part, and their products are also the same. So 1 times 2 is congruent to 7 times negative 4, or 2 is congruent to negative 28 mod 3. We can verify this one pretty easily. The top one, there's no need to verify, right? 3 is in fact precisely equal to 3, so it's certainly congruent to itself. Here we could see why this is true if we just do a quick check. 2 minus a negative 28 is 2 plus 28, or 30. And that's a multiple of 3. The theorem says, of course, we don't even have to check. Like, we're guaranteed that'll work. The next few results kind of rephrase some things we've already observed. Congruence classes partition the integers, right? We already know that the equivalence classes of any equivalence relation partition the set that it's on. Congruence classes or congruence relations are a special type of equivalence relation, always on the integers, so it's those congruence classes will always partition the integers. And so this just says it in the terms of using the notation and language of congruence classes. So it just says, suppose two things are equivalent mod n, and both of these values of r are between 0 and n, right? Like the remainder you get upon division by n is the same. Then those are going to be the same, right? They either overlap completely, right? They're non-overlapping. They are either the same equivalence class or they're disjoint. And then in part B, it just says we can do this division and get a remainder, right? We could figure out what A is equivalent to mod n. A is going to be equivalent to something between 0 and n. We think of those equivalence classes, like those sort of primary ones. You know, I picked up here, let's just start with 0, 1, and 2. I could have started anywhere. Like, let's start at -11 and find out what's equivalent to that. That's nothing wrong with that, but we kind of default to these ones. We call them the primary residues. And if you're working mod n, your residues only go up from start at 0 and go up to n minus 1. We could think of them as just the remainders that are possible when you divide something by n. And that's what we've got down here in Theorem 219. So there are always going to be n distinct equivalence classes from 0 to n minus 1. Again, you're going to see me use the overline notation because it's more convenient. And Theorem 220 simply says if we use like the division algorithm, right, and try to figure out what is A equivalent to mod n, suppose A is equivalent to R mod n, right, it leaves a remainder of R, and B leaves a remainder of R prime mod n, then these two remainders are the same if and only if A and B are equivalent mod n. This next definition just says, if you're looking for an equivalence class, everything will fit into one of these primaries, right? One of these guys. You don't have to go any further than that. If I can figure out that something is equivalent to, 13 mod 3, that means it was actually equivalent to 1. You could find one of those primary residues that it fits into, those primary equivalence classes. So in example 211, we're going to write down the congruence classes for n equals 5. This is pretty simple. So we call it z sub 5 or z mod 5z. You could really kind of take your pick as to what kind of notation you like. And we're just going to start at 0 and go up to 4. Every integer will fit into one of those congruence classes. So we have a set, right? I mean, here we wrote it down for z5, but for any n, we have a set. And it looks like kind of a finite set, although we remember that each one of those elements in the set represents infinitely many integers. But when you have elements of a set, it begs the question, like, oh, can these elements interact with each other? Can I add these elements together? Can I multiply them? And in fact, you can. And in fact, multiplying these whole sets together, these equivalence classes or these congruence classes, we can add and multiply congruence classes as a set together. And it's as simple as doing the arithmetic just on the integers themselves. So here we've defined these addition and multiplication on congruence classes. I'm using a little circle plus and a circle times here just to make a distinction, as these are operations on the classes themselves. And if I want to add two congruence classes together, all I got to do is take the integers, the individual integers, and add them, and then find that congruence class. So doing the arithmetic on the classes, which each of them contains infinitely many, is the same as just doing the arithmetic on the integers themselves. For example, in the set z plus 5z, I could take the equivalence class of 2 plus the equivalence class of 4. That's the equivalence class of 2 plus 4, or the equivalence class of 6. What equivalence class is 6? And, like if I look at that, right, I got the equivalence class of 6. We wrote down z5 up there. It's only from 0 through 4. If this is a well-defined operation, I ought to get a result that's already in my set. Is there another name for the equivalence class of 6? It's 1, yeah. Right, so 6 is equivalent to 1 mod 5, right? It's 1 more than a multiple of 5. So here's what this says. I just want to kind of parse out what this equation says, because it looks as simple as, the execution was as simple as adding 2 and 4 together, but I just want to make sure we understand what it says. It says you take any integer that's congruent to 2 mod 5, add it to any integer that's congruent to 2 mod 4, and you're guaranteed to get an integer that's congruent, sorry. Let me start over because I just misspoke. You take any integer congruent to 2 mod 5, add it to any integer congruent to 4 mod 5. You're guaranteed to the result will be congruent to 1 mod 5. So this is really a statement about arithmetic on sets. But it was as simple, the executing it was as simple as just the, working with 2 and 4 themselves. And this is how we might put together addition and multiplication tables. This is always a fun exercise. We're going to do an addition and multiplication tables for Z5. The addition is pretty simple. We're just going to do the addition on the integers and then make sure we're reduced mod 5. So adding 0 to everything is pretty simple. So 0, 1, 2, 3, 4. And the first column will be the same, right? 0, 1, 2, 3, 4. Now across the second row, the 1 row, this will be 2, 3, 4. Now I get to the end. 1 plus 4 is 5. But what is 5 congruent to? Mod 5. 0. Yeah. Then we add 2 to everything. So we get 2, 3, 4. We get 5, which is 0. And then 6, which is 1. Add 3 to everything. So we have 3, 4. 0. 3 plus 3 is 6, which is 1. 3 plus 4 is 7, which is 2. And then at the last row before, we start with 4. 4 plus 1 is 5, which is 0. Then we get 6, which is 1. 7, which is 2. 8, which is 3. But there's some cyclical behavior here, right? 0, 1, 2, 3, 4. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. It's the same cycle. It just starts in a different spot each time. Now let's do the multiplication table. Multiplying by 0, obviously pretty simple. So okay, multiplying by 1, also simple. So the second row and second column will be pretty simple. Pretty easy to fill out. Okay, now let's work across the 2 row. 2 times 2 is 4, so that's 4. 2 times 3 is 6, which is 1. And 2 times 4 is 8, which is 3. 3 times 2 is 6, which is 1. 3 times 3 is 9, which is 4. 3 times 4 is 12, which is 2. Mod 5. Let's fill out the last row. What do we get? Uh, 2 times 4 is 8. Yes, that's 3. And then what's next? 2. And then what?
So I'm going to guess 1.
It's 1. Why did you guess 1?
There's a pattern.
What's the pattern?
Well,
Is your mic on?
Yeah, I just saw a pattern on that last row where everything was kind of shifting over.
Oh, like descending?
Yeah.
Yeah, right. 4, 3, 2, 1. Yep. There's, there can be some patterns. The pattern is more recognizable when you're doing the addition, right? It's a little harder to notice when you're multiplying. But the bottom row is always going to be sort of backwards from the one row. And then in the middle, things kind of can be a little bit shifty. So one thing that is interesting, I think, if we ignore the 0 rows, right? Multiplying by 0 just gets you 0. But if you ignore the 0 rows in column, note that like every row has every number in it. That doesn't always happen. All right? When, the fact that every number is represented in every row and column in the multiplication table doesn't always happen. The fact that it does here has a lot to do with the fact that 5 is a prime number. We could, if we made this for, let's see. If we made this for, I'm going to do an extra. This is at no extra charge. Let's do this for Z6, Z mod 6Z. Right, so this is 0, 1, 2. And we'll do just the times table. Again, the 0 and 1 rows and columns are pretty uninteresting. Okay, now let's fill in the 2 row. 2 times 2 is 4, and that's 4 mod 6. 2 times 3 is 6, which is what? 0, yep. 2 times 4 is 8. 2 times 5 is 10, which is mod 6. What is it? What's our remainder when we divide 10 by 6? 4. There we go. Let's fill in the 3 row. 3 times 2? So it's 0, yep. Is your mic on?
No.
Let's just keep our mics on for a little bit while we're throwing out responses.
The other one.
So now the pressure is all on Andrew because his mic is on, and
That should be a 3.
this should be a 3. 3 times 3 is 9, which is 3, yep.
That would be 12, so it would be 6, so 0.
0, yep.
That would be 3 as well.
3?
Yeah, 3, right? 3 times 5 is 15, and that's 3 more than 12. Let's do the 4 row. 4 times 2.
2?
2. 4 times 3.
0?
4 times 4.
4?
Because that's 16, which is 4 more than 12, yep. And 4 times 5.
2?
2, it's 2 more than 18. And then the last row.
4.
4? 3?
3.
4?
2, yeah. Yeah, so no matter what your n is, the bottom row is always like 5, 4, 3, 2, 1, or n minus, n minus 1, n minus 2, n minus 3, right? Just counts down. So the one row counts up, right? The bottom row counts down. And then we have weird stuff going on in the middle. I I'm going to stop and make a couple observations that might be interesting. We'll see. Not necessarily the pattern, although there is one, right? If the 2 row looks a lot like the 4 row, right? But just look at that 0 where it is right now. What that 0 there tells us is that 2 times 3, the equivalence class of 2 times the equivalence class of 3 gives you the equivalence class of 0. As a set, when we think about doing operations on elements of a set, 2 is not equal to 0, right? In this set, 3 is not equal to 0 in this set. Yet we have found 2 non-zero things we multiply together and get 0. That doesn't often happen. We're not used to that happening in mathematics. So we call these, we say that 2 and 3, these equivalence classes, are 0 divisors in Z mod 6Z. So that's an interesting thing that happens. Also, I'm going to look at, take a look at this guy right here. So this says that 3 times 5, the equivalence class of 3 times the equivalence class of 5 is equal to the equivalence class of 3. I took 3 and I multiplied it by something and I got itself. Usually what we're used to when that happens is that this thing would be like 1 or something, but that's clearly not 1, right? So it's not that 5 is not an identity. It's not that always happens with 5, but it's just sort of odd behaviors that we get when we're looking at these. So sometimes we get these 0 divisors. This is not something that happened. We had no 0 divisors in Z mod 5Z, right? If we go back and look at that one, whoops. 0 only showed up when I multiplied something by 0, right? And that's kind of what we expect. So we had like nice, more expected behavior in Z mod 5Z that has everything to do with the fact that 5 is prime and 6 is not. So because 5 is prime, there are no 0 divisors there. That makes it special. In fact, we call this, we give it a special name. We say that Z mod 5Z is in fact a field because there are no 0 divisors. It's an integral domain and it's a field. Also, if I take any integer, any equivalence class, like say the equivalence class of 2, and I want to know, what do I multiply by to get 1? I can find it, right? I multiply 2 by 3 to get 1. And in a sense, 2 has a multiplicative inverse, right? I can get back to 1. I can do that for any of these. That's always true for Z mod PZ, like for a prime. But if you look at what we did with Z mod 6Z, if I say, what do I multiply by 2 to get myself to 1? Nothing. 2 does not have any inverse in Z mod 6Z. So, what's prime and what's not prime has consequences for how Z mod NZ behaves. Okay. So that's fun. And I think this example will help you out with maybe the last problem on the test. I think there's one problem where you're asked to make a multiplication table for some modulus, Z mod NZ of some kind. So just some definitions and some new terms. If B is equivalent to R mod N, we say that R is a residue of B. So these congruence classes, we also refer to them as residues, mod N. And that term residue really kind of comes from like remainder, like what's left over. So that's sort of like the, I guess, genesis of using that term. We have a complete residue system if all the equivalence classes are represented. Now the general residue system, what we call the primary residue system, the one where we just say, if I want Z mod 5Z, I'm just going to go from 0 to 4. Or Z mod 6Z, I'm just going to go from 0 to 5. That's the primary. And usually there's not much reason to use a residue system that isn't primary, but you certainly can. Any complete residue system will work. So if we think about Z mod 6Z, the primary for Z mod 6Z is just 0 through 5. But here's another complete one. The primary is always complete, but here's another complete residue system. So instead of 0, I'll take any multiple of 6, say 36. 1 more than a multiple of 6, 13. 2 more than a multiple of 6, 44. Let's see, negative 16 is congruent to 3 mod 6. 22, negative 25. That is a complete residue system. It is, you can check. You'll see that 5 and negative 25 are congruent to each other, mod 6. 4 is congruent to 4 is congruent to 22. 3 is congruent to negative 16. There's not much of a reason to use a complete system that isn't the primary, right? Like, it just seems silly. But it's true. You can do it. Now, a reduced residue system is one where we just take the ones that are relatively prime to the modulus. So a reduced system mod 6. And I'll start with the primary. Knock out anything that shares divisors with 6. You always knock out 0. 0 is never part of a reduced system. 1 is always in the reduced system because 1 doesn't share divisors with anything other than 1. But look, 6 is divisible by 2 and 3, so we can't include that. We can't include 4 because they share a common divisor of 2. So the reduced system mod 6 is just 1 and 5. And now, if we go back to that multiplication table that we made for Z mod 6Z, 1 and 5 are the only ones where we were able to, first of all, find something to multiply by to get me back to 1. And they're also the only rows where everything is represented. And that has a lot to do with the fact that it's relatively prime to 6. In the last row, if you make a multiplication table, the last row, we said it always counts down. And I'm just going to, the implication there is that this very lower right corner is always a 1. So like n minus 1 times n minus 1 is always going to give you 1. 5 times 5 is 1 mod 6. That hopefully won't be surprising when we consider the fact that in Z mod 6Z, 5 is equivalent to negative 1, right? Being 5 more than a multiple of 6 is the same as being 1 less than a multiple of 6. So 5 times 5 is like having negative 1 times negative 1. Of course, that's negative 1 times negative 1 is always 1. So, like if I'm working on Z mod 13Z, and I want to know, oh, what's 12 times 12? That's going to be 1. It's negative 1 times negative 1. Okay. A couple more theorems that we're not going to prove. If we have a complete residue system and A is any old integer, A will be congruent to one of those. So even if it's not the primary system, A will be congruent to one of those. That makes sense because we know that residues partition the set of integers, so it's just sort of another restatement of that. If we have a reduced residue system mod n. So here's what I want to point out here. First of all, it's reduced, and there are k elements in that, and it's mod n. There's obviously not going to be n, right? We're only taking the ones that are relatively prime. So k is going to be less than n for sure. If a is an integer that's relatively prime to n, then it will be in one of these residues. It will be congruent to one of these residues. Meaning, like, if I go up here to, we found the reduced system mod 6. Take any integer that's relatively prime to 6. Any integer that shares no divisors with 6. Like, I don't know, 101 doesn't share any divisors with 6. That'll be congruent to one of these two. Any any integer that's relatively prime to 6 will be congruent to one of these two prime reduced residues. Okay. And theorem 222 is kind of cool. It says, let's say you have a reduced residue, so you're taking just the relatively prime ones, mod n. Then if you take any integer relatively prime to your modulus, you could zap every element here and create a new reduced system. So, example. The reduced system mod 6 is 1, 5. We can make another reduced system. So the greatest common divisor, let's pick an integer that is relatively prime to 6. Some integer that shares no divisors with 6. Something that that's not divisible by 2 or 3.
Has to be odd. About 11.
11?
7.
7? Okay, we'll do them both. So I take 1, 5. If I multiply this by 11, I get 11, 55. That's another reduced system. If I take 1, 5, multiply it by 7, I get 7, 35. So these are reduced systems. And in fact, if we reduce mod 6, right, 11 mod 6 is 1, 55 mod 6 is 11 mod 6 is not 1. That's 1 mod 5. 11 mod 6 is -1 or 5, actually. Okay. And 55 mod 6 is 1, because 54 is a multiple of 6. 7 mod 6 is 1. 35 mod 6 is 5, because 30 is a multiple of 6. So they all reduce to the same set. Notice in this case, in the top one, like the order was reduced, right? I multiplied through. It's not that I multiply anything and the order is preserved, right? I got 11 and 55 and that kind of jumbled things up. It just sort of reversed them. But I still got a primary, or a reduced system, rather. And that'll always be the case. If you take any reduced system, just multiply it through by something that's relatively prime, and you'll get another reduced system. It's also true for any residue system, any complete residue system. So if I take the primary residue system, mod 6, and let's say I multiply by 7, I'm picking something relatively prime to 6, we get 0, 7, 14, 21, 28, 35. And I think here the order is preserved, right? 7 is congruent to 1, 14 is congruent to 2 mod 6, because 2 more than 12, 21 is 3 more than 18, 28 is 4 more than 24, 35 is 5 more than 30. If I took this and instead multiplied by 11, and then reduce these, right, these would be 0, 5, 4, 3, 2, 1. But I still got a complete system. The same thing is not true if you multiply by something that is not relatively prime to 6. And the easiest example I can come up with to convince you of that is that if I multiplied by 6, then they're all 0 mod 6, right? You end up with multiples of 6, and those all reduce to 0. So. How we doing? Okay. All right, so in the time we have left, I thought we'd get a start with a little bit of counting. We're going to do some basic counting principles. If you've ever taken a stats course, then at least the beginning parts of this chapter will be probably familiar, but still enjoyable. We're going to do some basic counting. And then things, okay, so first, before we do some basic counting, I just want to let you all know that counting in general, like in mathematics, we call this area combinatorics, basically just counting things, all right? But it is an area of math where the questions are really easy to ask. Like, we totally understand what question, what we want to find out. We don't really have to parse it out that much. We're like, oh yeah. But then they are surprisingly interesting, sometimes difficult to answer. It's a super fun area of mathematics. So I hope that this chapter will be fun. It'll also probably be a little bit frustrating because it can be frustrating when we know exactly what they're asking. We're like, I can't kind of separate things out. But we're going to develop some tools to kind of help us be smart about how we think about counting things. Most of the types of questions that we answer in combinatorics begin with, how many ways can you do, and then they describe something. So here's sort of an introductory problem. Suppose one day you decide, I'm just going to toss a coin and roll a die. Mark down what happens for some reason, for reasons, right? You got a reason that you want to do this. So if we toss a coin, right, I'm either going to get heads or tails. And I'm writing the set of outcomes as a set, right? Because it doesn't matter which comes first, right? Those are just the outcomes. And then if I roll a die, like a regular, say, a 6-sided die, right, I'm going to get something 1 through 6. I'm going to get one of those. So if I'm trying to think about, well, what are the possible outcomes, like as a sequence, that could happen? So I toss a coin first and then I roll a die. We can kind of visualize a set of outcomes. As here's our starting point. The first thing we do is toss a coin. I'm going to go down one of these branches, right? And then as soon as I do that, I'm going to roll a die. And I'm going to go down one of these branches. So we kind of have like a little tree to describe this sequence of events. How many possible outcomes are there for this sequence of tossing a coin and then rolling a die? Say that. 12, yeah. Right, there's 12 paths, right? So like one path I could go down might be I get a tail and then roll a 2, right? But there's 12 distinct paths I could go down. And this is sort of an example or a visualization of what we call the multiplication counting principle. So if we have a sequence of events, E1 through EM, and let's say the first event can occur in N1 number of ways, and the second event can occur in N2 ways, and the third event can occur in N3 ways, once those first events have happened, then the number of outcomes for the whole sequence is you just multiply the number of ways each of those individual events could have occurred. And that's what we get here, right? So there's 2 ways for the coin toss to come up, 6 ways for the rolling the die to work, and then that means the total number of outcomes for the sequence is 2 times 6, or 12. One important example that comes up a lot is rolling a pair of dice. So mathematically, there's really no difference between rolling 2 dice at the same time and seeing what comes up on each die, and then rolling 1 die, marking it down, and then picking that die up again and rolling it again so that you have 2 die outcomes, right? Mathematically, they're equivalent. it is really important to know that we have to think of these two dice as distinct and the outcome of each dice to be different, to be distinct outcomes. Like if I'm rolling a pair of dice, it's easier if I think of as rolling one die that's black and one die that's white. And so each outcome will be one of these 36, right? Because there's 6 ways for the first die to come, 6 ways for the second die to come out. That gives us, using the multiplication counting principle, 36 outcomes. Now, you might question why we need to do this. If I roll a 2 and a 3, like who cares which one comes up a 2 and which one comes up a 3? And, if you're actually rolling a pair of dice in the event of like playing a game or something, if you're playing backgammon or whatever, maybe it doesn't matter in how it's interpreted in the game. However, from a counting and probability perspective, it matters very much. We'll note that there are 2 ways to get, say, I don't know, a 1 and a 2. Right? I can either get 1, 2, or I can get 2, 1. And in the diagram, they're here and here, right? 2 ways to get a 1 and a 2. There is only one way to get double 2s. They both have to come up 2. Right? You can't replicate double 2s. Right? Each die. So from a probability perspective, it definitely matters. Right? The probability of getting, we're going to do more with probability later, but just from the basic concept of probability is how many ways can my event happen versus how many total possible outcomes there are. So if I look at this, I say, oh look, the probability of getting just a 1 and a 2 is 2 out of 36, or 1 out of 18. But the probability of getting double 2s is 1 out of 36. So it does matter very much which die comes up in which order. Let's do some stuff with the multiplication counting principle. So let's say we have some set S with n elements, and we have another set T with m elements. How many functions are there that map from S into T? So, and then we'll look at how many one-to-one functions. But first, how many functions? So we're working with finite sets now, right? So we're not thinking about functions that map reals to reals. We've got a set S with just n elements, and we just want to map them into the set T with m elements. So each of the n elements of S can map to any of the m elements of T. So I'm making a little space here for each of my elements of S. So I'll call this element S1, S2, S3, and all the way up to Sn, right? So each element of S is listed there. So I pick S1, right? I've got that element. I want to send it to something in T. How many choices do I have?
As many elements as there are in T.
Yeah, yep. And what's that here?
M.
M. Right, so I've got M choices. So now I've picked that, right? There are M choices. Now imagine we picked whatever one I'm sending it to, and we move on to S2. How many choices could I pick?
And was already taking up that slot.
Well, it's
Or
not
S1 or
necessarily, this is any old function, right?
Because I'm wondering if it could also be m, or would it just be m minus 1?
Yeah, so this is, so that's a good question. This is just any function. Nothing special about this. We can double up on outputs in a function, right?
Okay.
It's okay for every element of S to map to the same element of T, right? So how many choices?
Total?
Yeah.
Times that.
Yeah. So we have M, and then on down the line, right? They're all M. And there are n of these elements of S, so we have m raised to the n power functions that map S to T. Now let's look at the second question here. How many of them are one-to-one?
Can I just ask you a question real quick?
Yeah.
Why is it m to the power of n rather than n times n? In the previous example, it was the set of possibilities times the set of possibilities.
Yeah, so that's what we have here. But we're multiplying m by itself n times. Right, like here,
Okay.
yeah, we have n factors of m.
Okay, so it's my misunderstandings in how the functions are mapping to each other. Okay, I understand.
Okay. So how many one-to-one functions? Again, I'm going to make a slot for each element of S. So here's S1, S2, S3, all the way up to Sn. And I'm starting fresh, right? I've got S1. I would just want to send it to some element of T, and there are m of them to choose from. So this starts out the same way, right? I got m choices. But now I want this function to be one-to-one, which means we cannot double up on outputs, right? So once I've picked, if I have picked whatever output I'm using for S1, how many are left for S2?
m minus 1?
M minus 1, and your mic is on. Good, great. And, sorry, I just get vigilant about checking microphones because I know it can be frustrating to not hear when you're not in the room. All right, so now imagine we picked the output for S1 and S2. How many choices are left for S3?
M minus 2.
M minus 2, yep. And then on down the line, right? M minus 3, M minus 4. So the question is, how many choices remain for Sn?
I don't know if you can describe it this way, but m minus n minus 1.
Yeah, M minus, and then parentheses N minus 1, right?
Yep.
Like we're subtracting, yep, and we're just sort of noticing this pattern, right? S2 was M minus 1, S3 was N minus 2. So that just continues. So, and then we just multiply these together. So whatever this product is, that's the number of one-to-one functions. Okay. So that's a start. We're just about out of time, so I'm going to wait and hold off on the rest of this. We'll finish this on Monday and probably do some more counting. But also on Monday, bring questions. So between now and Monday, please get a start working on that take-home test if you haven't done so already. I'm going to start class just taking questions. If you're stuck on a problem, kind of giving some pointers, maybe giving a nudge in the right direction on some of those problems. And then we'll continue on with counting stuff. Okay. All right. Enjoy the rest of your day, everybody.